Hi, I'm Jeff Krause, and my research is on an anomaly detection algorithm using multiple time series datasets for network monitoring. Let's get started. Light Reading, a business insights and research company, estimates approximately 5 network outages or performance degradations occur per year, resulting in losses for network operators totaling $15 billion. This research will examine the application of an anomaly detection solution to automatically identify anomalous trends, thus reducing costly outages or performance degradations. This research focuses on a wireless carrier with a 4G LTE high-speed network. The network is composed of many individual markets. Each market coverage area is composed of hundreds of cell towers which transmit customers' wireless traffic over backhaul links to a central MITSO or mobile telephone switching office. At the MITSO, there is a cell site router which aggregates the traffic for the specific market and passes it to the other infrastructure such as the SGW or serving gateway, which then allows this traffic to pass onto the network core and out to the internet or the services the customer is accessing. This research focuses on the available metrics from the cell site router to determine the stability of the market. A standard protocol called SNMP or Simple Network Management Protocol is used to collect these metrics. It uses an SNMP puller device which generates SNMP GET requests to the router and receives a response with the requested data. The research data is collected from the SNMP puller and is focused on 4 metrics: BPS or bits per second and bytes. BPS is a measurement of the total throughput or speed being observed in a market, whereas bytes is a measurement of total volume being observed. 6 months of data on 15-minute intervals is extracted over 5 selected markets, resulting in 20 time series datasets, each with 17,568 data points. With the 20 time series datasets extracted, they are then placed in one of 3 buckets. The first is the original unmodified time series. The next is aligned on day of week, where, for example, all Tuesdays are aggregated into their own dataset, all Wednesdays into theirs, etc. This results in 140 day-of-week aligned time series datasets, each with 2,496 data points. The last group is aligned on time slice. For example, all 12 a.m. time slices are aggregated into their own dataset, 12:15 a.m. in another, 12:30 a.m. in another, and so on, across all days. This results in 1,920 time series datasets, each with 183 data points. A summary of the forecast type being used based on the 3 buckets identified can be seen above. Approximately 15 to 18% of the data is used for the initial training of the forecast model. In total, over 837,000 forecasts will be executed in this research. Each time series dataset is ingested into the statistical programming software package called R. Then, using the Forecasting Principles in Practice, or FPP package by Professor Rob J. Hindman, and a few lines of code, a forecast using seasonal trend decomposition procedure based on the lowest smoother and or exponential smoothing state space model will be used to produce the forecasts. The actuals or observed data identified by the black line is used to produce the forecast. The forecast is composed of the fitted or forecast mean, the red line, and the upper and lower 99% confidence intervals identified in the green and purple lines. The algorithm uses a one-step ahead sliding forecast window. It will grab the next new observation and drop the oldest observation between performing forecasts. Upon grabbing the new observation, it will be compared to the mean forecast value. The difference between the actual observation and the forecast value are called the error or residual value and will be used to calculate the root mean squared error, which will be used as one criteria to determine the effectiveness of the forecasting model. An anomaly is recorded if a new observation extends above or below the 99% confidence bands. Anomalies will be validated by extracting high-severity customer tickets, network operating center tickets, and change request tickets. The tickets have a created date and a restored date, which will be used to produce a reference of ones and zeros to identify the total time slices covered by a ticket. This reference will then be compared to the anomalies flagged by the algorithm. This will allow a truth table to be created and provide a method to measure the effectiveness of the anomaly algorithm as it relates to the tickets. Recall, precision, specificity, and accuracy will be used to compare the three forecasting methods. Initial results of the algorithm produced many more anomalies than anticipated. The chart above displays about 2,200 anomalies obtained using the 99th percentile criteria alone, which translates to about 12 alarms per day on average. For the algorithm to have practical applications as an automated alarming system, it requires additional tuning. Expansion and excursion are two configurable options to tune the algorithm. The yellow boxes identify observations which extended beyond the bounds of the 99% confidence bounds. Expansion measures the percentage of expansion the observation has beyond the range between the 99% confidence band and the forecast mean. This allows for an expansion threshold percentage to be set, allowing the administrator to use discretion over what should be recorded as an anomaly. Excursion is another method that uses moving averages to smooth out the anomaly to reduce its effects. For example, an excursion of 2 would reduce the expansion by a factor of 2. An excursion 3 would reduce by a factor of 3, and so on. When using tickets as the authoritative criteria to measure the effectiveness of identifying anomalies, there are mixed results. The tables displayed for each market represent the results of the algorithm. The rows indicate the method for identifying anomalies, with 1 indicating the expansion method and 2 through 20 being the various factors of the excursion method. The columns indicate the threshold to detect an anomaly from 0, implying no expansion tolerance, to 2, implying suppress the anomaly unless it exceeds 200%. Precision of the markets varied greatly. Market 1 did poorly since it had only 1 ticket over 4 time slices without any adjoining anomaly within 20 time slices. Market 4 did extremely well as the majority of large spikes in the data coincided within 20 time slices of a ticket. So the value of the results is contingent on placement or existence of the ticket. This is also evident in the recall. With excursion 20 with 0% threshold, the amount of true positives increase and false positives decrease, since the anomaly region is stretched over a larger section of time slices and more likely to overlap with a ticket time slice. To further examine the results, I developed a dynamic graphic visualization environment that allowed me to identify specific time slices to view, along with tickets and thresholds for anomalies. This allowed maximum flexibility in reviewing various size samples of data. From this, I discovered the majority of the anomalies fall outside the ticket time slices, and many ticket time slices had no visible impacts to the metrics being measured. In other cases, I observed a clear impact to the metric, but the ticket fell outside the time slices of the anomaly because the ticket had erroneous time frames. This led me to the conclusion that the tickets required additional scrubbing and classification to bring more value to the validation process of the models. Using the aforementioned visualization environment, I was able to manually review the datasets and identify the expansion method seemed to provide a good balance between capturing significant anomalies and reducing overall total anomalies. The chart provides the total anomalies detected for each method per market based on the thresholds between 150 to 300%. The TS, or time slice method, appears to perform the best overall, but this is skewed due to how well it performed with Market 3, which had the most variability. Comparing market to market, The SF, or straight forecast method, appears to perform a better job and is much simpler to implement as well as to interpret. Overall, I am pleased with the performance of the anomaly detection algorithm. With visual validation, anomalous trends can be tuned using expansion and excursion threshold criteria. This will result in less false positives needing to be investigated by field engineers. The ticketing validation approach opens up opportunities to provide better classification of tickets as well as ensuring better accuracy. Using the SF, or straight forecast, appeared to provide the best results using the STL and ETS models provided in the FPPR package. This is somewhat surprising, as the initial expectations of using day of week or time slice would be to reduce the overall variation in the data, but due partially to the growth in the network over time, this was not the case. Additionally, the straight forecast was easier to implement and understand, as well as provided the best root mean squared error result.